Historically, Bernoulli's principle has been an easy explanation for how lift is generated, how birds fly, and how airplanes fly. A pressure gradient washes over a airfoil or a wing, and the difference in pressure on the top and the bottom allows for a lift force to come up and lift the plane or the bird into the air. However, this is not quite what happens. Thin airfoil theory is a much more accurate depiction of how lift actually works than Bernoulli's. This only works at low angles of attack. Within this video and within this project, we hoped to model bird wings as airfoils using thin airfoil theory and compare predicted lift coefficients to experimental values in order to better understand how gliding is achieved in a 2D flow. In order to achieve flight, there are three basic forces that need to be balanced: weight, drag, and lift. These last two are incredibly difficult to compute, as both lift and drag require coefficients that usually are found through experimental data. However, there are several assumptions that we can make that will allow us to estimate both of these coefficients, such as thin airfoil theory. Thin airfoil theory was developed in the early 20th century and simplifies aerodynamics by modeling a thin airfoil through a vortex sheet on the camber line. This theory allows us to make several assumptions: that at small angles of attack, flow is inviscid, incompressible, and irrotational. These assumptions are essential for us to predict the lift of our airfoil models and understand at which angles the flow separates and flight stalls. Lift and drag can now be distilled into equations based on four factors: the 2D cross-section of the airfoil, the airfoil's total surface area, the density of the air around the airfoil, and the air velocity attacking the airfoil. With these assumptions in mind, the first major task is building the aerodynamic model, beginning with a cross-section of the airfoil in the x and z axes. Instead of relying on a single analytical formula, we extract the actual shape from airfoil images and then fit splines through the boundary points. These splines allow for a smooth interpolation of the geometry and, more importantly, obtain the derivative of the surface. That derivative is what thin airfoil theory needs to compute the A values, which then give us the lift and moment coefficients. These A values are known as Fourier coefficients, which allow us to solve for the coefficients of lift and pitching moment. Tolerances were used to avoid singularities at the leading edge, which would have caused major problems. Choosing the airfoil itself matters because the lift curve slope and the pressure distribution depend heavily on the shape. In our case, we focused on a standard NACA profile. Once the boundary data is processed, the code automatically scales everything to the correct chord length and converts the spline into the mathematical form needed for the aerodynamic integrals. Now, one limitation of thin airfoil theory is that it assumes inviscid flow. That means drag cannot be computed directly. This is a consequence of D'Alembert's paradox. So instead, we estimate drag using two pieces: the induced drag, which comes from the lift distribution, and an average parasitic drag coefficient measured experimentally through wind tunnel testing. This allows us to approximate total drag well enough for flight dynamics modeling, even though viscosity isn't explicitly included in the theory. Once lift and drag and moment are known, they feed into the equations of motion. The model becomes a system of coupled ODEs because the force depends on the wing's XZ position, its velocity, and its angle of attack. These interactions mean there's no realistic closed-form solution, and multi-step methods don't help much because the future flow conditions may change from step to step. For that reason, a single-step integrator is the practical choice. We chose the fourth-order Runge-Kutta method, RK4, because it strikes a very good balance between accuracy and implementation cost. In the code, RK4 is used to advance the state of the system one time step at a time. The position, the velocity components, and the rotation all get updated by evaluating the force model at 4 different stages inside each step. By combining those 4 estimates, RK4 achieves high accuracy without needing millisecond time steps. Altogether, spline-based airfoil geometry, thin airfoil theory, the drag approximation, and RK4 integration form a complete pipeline that lets us simulate the flight behavior of the wing cross-section over time. With thin airfoil theory, understanding how the angle of attack shifts is imperative. In the first two flow cases, the angle steadily drifted towards zero over our time interval, which makes sense. Without gravity-induced torque or nonlinear aerodynamic effects, the airfoil simply tries to align itself with the incoming flow. But this exposes a major limitation. Once the angle grows too large, even briefly, thin airfoil theory stops being reliable and the model can't accurately predict the forces anymore. That breakdown is tied directly to how sensitive the system is to angle of attack, especially over longer time intervals. Velocity brings out an even more serious issue. Because the flow field is held constant and the model doesn't include the mechanisms that would naturally limit acceleration, the relative velocity can grow without bound. In some of the simulations, it increased so rapidly that it effectively went to infinity near the end of the run. This isn't a physical effect, it is a numerical consequence of the model being stiff. RK4 works well for smooth, well-behaved systems, but here it amplifies small oscillations until the solution breaks apart. This is part of the trade-off. The model is general enough that we can apply it to different flow conditions, different airfoil alignments, and different initial states without rewriting the underlying equations. That flexibility is one of its biggest advantages. But the same generality means it lacks the stabilizing features like nonlinear lift behavior, more realistic drag growth, and angle-dependent dampening that would keep long-term simulations well-behaved. As a result, it performs best on short-duration problems where the angle stays small and velocity doesn't have time to diverge. In the third case, where the vertical flow component was increased, these weaknesses became unavoidable. The angle started outside the valid range of thin airfoil theory, the forces escalated rapidly, and the integrator couldn't keep pace with the changing dynamics. Even though the structure of the equations looked similar to the milder cases, the system behaved like a textbook stiff ODE. Without an adaptive solver designed for the stiffness, the model simply wasn't capable of producing meaningful results past the first moment of motion. Altogether, the three cases make the strengths and weaknesses clear. The model is adaptable, interpretable, and efficient, but isn't built for long-term prediction or for situations where angle or velocity stray beyond thin airfoil assumptions. To push the simulations further, the next steps would involve switching to a stiff integrator and adding the physical effects that the simplified theory can't capture on its own. To sum up our methods and findings, we used a thin airfoil theory to allow for a modeling of a very complex problem, namely aerodynamics. We used edge detection and splines in order to find our lift and moment coefficients, which led to our estimated drag coefficients. When combining this with a struct function and an iterative RK4 method, this allowed us to figure out that this is a very stiff ODE. In the future, we would like to explore this stiff ODE more and find a way to solve it. In the meantime, thank you so much for watching. We hope you enjoyed the video.